Hello and welcome to another teaching guide for EE140. Today we will be looking at Gaussian surfaces in dielectric coaxial cylinders. For this particular question, we will be looking at a long dielectric cylinder which has a radius of A, and we know from this question we are given a dielectric constant of mu r1 that is non-uniform, and this non-uniform volume charge density is given as rho equals to alpha r. For the other dielectric material that is between A and B, which is this region right here, it has a dielectric constant mu r2, but this time it is uniform charge density rho naught, and the outer shell is grounded as shown by this arrow. Okay, so now that we know all the information that is given in the question, we would need to know the equation that we would be using to solve this particular question, and that equation is the closed loop integral d dot dA equals to q enclosed this formula we would be using basically is saying that d, which represents the flux density, A would be a small change in surface area, and Q is basically the charge that is being enclosed by the Gaussian surface that we would be selecting. So for part A, we need to find the electric field in all regions. For the first region, we would be looking at where R is less than A, and we would be looking for the electric field. So how do we find the electric field? The electric field can be obtained from D, which is the electric flux density. So D equals to the permeability of the material, the dielectric constant, and for this will be mu r1 because we are looking at the dielectric material which is inside of A, E, and then since we are looking at a cylinder, it would be 2 pi r L, and we can take this and equate this to the charge, which equals to the integral of rho dV, and then just writing this out, where rho dV would equals to alpha r. And so for the volume, we would be taking basically the perimeter of a circle, which would be 2 pi r, and we are going to multiply that with the length of the cylinder with respect to dr. The integral from 0 to r, because our Gaussian surface is not up to A, but it is a radius of lesser than A. And from the equation above, we just pull out all the constants, which would equal to 2 pi alpha L, and then we integrate the rest from 0 to r, and both the r's from the top can be multiplied together, so that will give us r squared dr. And from here, when we integrate it, we get 2 pi alpha L r cubed over 3 bracket 0 to r, and just by doing math, we will get 2 pi alpha L r cubed over 3. And that is just for your radius that is less than a. So finishing this off, we can see that the electric field where the radius is less than a equals to 2 pi alpha L r cubed over 3 mu naught mu r1, and with the direction pointing to r hat. So for the second part of this question, we will need to find the electric field that is in between A and B. So we do this by taking A lesser than R lesser than B. Similarly to what was done in the top, we would just take the enclosed integral d dot dA equals to Q enclosed, and this would simply become the permeability, the dielectric constant, but this time it's R of the second dielectric material, E field, and same thing from the top, 2 pi r L equals to the enclosed charge, which for this particular question would need to include the charge that was found where the radius r was less than a. So what we do is we just copy this particular electric field over here, but this time replacing the radius r with a instead, because the charges are only up to a for the first dielectric material. And so let's just do this first because it's easier. 2 pi alpha L with a bracket of a cubed over 3. And since the question did say that it is a uniform charge density of rho naught, we can just skip the integration and sub in the values immediately. So it'll be rho naught, but the volume would just be pi multiplied by r square L. But just because we are trying to find the charge that is found between A and B, we can say that the radius of our Gaussian surface that we are going to be choosing can deduct off A in order to give us the entire charge that is enclosed between A and B. So what this would look like is basically copying from the top 2 pi alpha L bracket A 3 over 3 plus rho naught pi r square minus a square multiplied by the length. So now to move all the terms to one side, we can write E is equal to 2 pi alpha L bracket a cubed over 3, putting that over this whole thing here, which would be 2 pi RL mu naught R2 plus rho naught pi R2 minus A2 multiplied by L, and that whole thing is over 2 pi RL mu naught R2, and this whole thing bracket R hat. So simplifying this, we can just write it as these terms cancel out. We would just get alpha a cubed over 3 mu naught R2 R, making this longer, plus like terms cancel out, and we would get rho naught R2 minus A2 over 2 RL mu naught mu R2, and just the whole thing is with respect to R hat. Okay. The last thing that we need to look at is the radius, where it is greater than B, which should basically mean the grounded conductor that we're trying to find. And we know that the electric field for any conductor that is shielded or grounded would be just 0. So pretty simple, I mean, for that to be 0, because it is conductor that is grounded, therefore it is shielding the internal dielectric materials from the outside. So shielded. And that is the end for the first problem, which is finding the electric field in all regions. So for the second part of this question, we will need to sketch E as a function of R. As you can see, I have already pre-drawn the axis for this plot. So how do we go about solving this particular question? Remembering the answer that we had earlier. So for your radius, I'll write it over here, where R is less than A. Our final answer was E equals to AR square over 3 mu naught mu R1 R hat. So very quickly, all we have to do to be able to plot this particular graph is to take our maximum radius for this equation and sub it in, and for the maximum for this equation would be 8. So we would just take equals to alpha A square over 3 mu naught mu R1, and that would be our first plot that we need to draw. So it will be something like this, going up in terms of a square function, and this one would be coming down this way, and that would be A. And from here we would just draw a dotted line so that we know that this is alpha A square over 3 mu naught mu R1. Let me extend this up a bit further, something like that. So like a straight line, you guys get it. Okay. And how do we know that this is going in this direction, this particular shape? And how do we know that it's square? We know this by looking at the power of A. So let me change color real quick over here. So A, this over here by the red circle. So that red circle means a square plot. And how do we know it's going up like this way, like a smiley face, like half a smiley face? It's because it's positive. It's a positive number. And very simply, so for a square plot, if it's a positive number, it'll be this, like a smiley face, and this is a positive. If it was negative, it will be this, a sad face. So this is for negative. Okay. And we still have a second dielectric material that we need to talk about, which was between A and B. So how do we find the first value for this? We will take the equation that we had solved previously in part A, and this would be A lesser than or lesser than B, E equals alpha A cubed over 3 mu naught R2 R plus rho naught bracket R square minus A square over 2 R epsilon naught minus mu R2. Okay, and since we need to find how it looks like at A, we will just sub A into all the R values. So sub A into, let me just call this 1 into 1. And by doing that, we get the EE field equals to alpha A cubed over 3 epsilon naught mu R2 8, and like terms cancel out, this cancels, and the term at the back is just basically plus 0. It's because when you sub A into here, this becomes A square. So A square minus A square will be 0. So 0 over some number will be 0. And that's why it is 0 at the back. So now we have this answer, alpha A square over 3 mu naught mu R2. We just take this and write it here, and there's going to be a jump. Okay, so let me just write this down this way. It's not connected, so it might be somewhere around here, this point. Okay, you can just draw a dotted line there, and we can just say that this is alpha A square over 3 mu naught mu R2. The reason for this jump is due to the change in the dielectric material. So jump is due to the change in material. Okay, so this is very important. It's not connected, and you have to watch out for this every time. So to find how the shape will look like and at what point will it be at B, we can look at it at below, where we sub B into 1, and from here we would get something like this. E equals alpha A cubed over 3 mu naught mu R2 B, let's extend that, plus rho naught B square minus A square over 2 B mu naught mu r squared. Oh, a correction earlier over here. This is not a minus. They are just one term together. And this would be the value that we find at B. So looking at this, we know that this is a cubic function by the power that is seen over here, by the red circle. And knowing cubic functions, we can say that for positive, this is how they look like. And for negative, they look like this, kind of like the mirror image of it, something like that. So going up here at our plot, since it is positive, we can say the plot goes like so. And this point value here would be whatever we solved below. And this point is basically when I say I sub B into the E field equation between A lesser than R lesser than B. For C, it will just be a straight line from B as exactly on the axis. And the reason for that is the electric field is 0, so there is no shapes that will be drawn. It's just a straight line flat on the axis. And that's it for part 2 of the question. For the last part of this question, part C, they're asking us to find the surface charge density when R equals to B. So right now, we would have to find the total induced charge. And from this, we know that induced charges are basically the opposite of the charge that we have. So from this, we can say the induced charge is equal to negative 2 pi AL A cube over 3 plus rho naught L pi B square minus A square bracket. And for this is when R is less than A, and this is when A is less than R, less than B. So why do we include both of the charges? The reason for that is that we need to include all enclosed charges when we are trying to find the total induced charge. So now that we have the induced charge, all we have to do is put into the formula where charge density, surface charge density is equals to Q induced over the surface area of a cylinder, and this would basically become Q over the perimeter of a circle multiplied by the length of the cylinder. So over here, we can write this out as in negative 2 pi AL bracket A cube over 3 close bracket then this whole thing is over this 2 pi BL, and I'm adding the negative sign in, so this one will become a negative rho naught L pi B square minus A square over 2 pi BL. So simplifying everything, I can discard these two, I can remove that, and over here I can remove this, and this, and I can technically remove this as well. So the final answer will become A, which is not a alpha. Let me recorrect that. Alpha A cube over B3 minus rho naught over 2 bracket B minus A square over B. And that is the final answer for surface charge density when R equals to B. So thank you for watching, and that's the end of this video.